So we're using tree diagrams to create our sample space, and we've seen how to make a very simple tree diagram for something as easy as heads and tails. And then we saw a two-child example, which actually could have been two coin tosses just as easily. So imagine H and T in place of M and F, and it would work the same way. So now we want to kick it up a notch for three. So we're going to have three, and this particular one, we're going to do, again, three biological sexes of children. But again, it could work for three true false questions. It could work for three right and wrong questions. It could work for three coin tosses. I mean, the theory still works no matter how you're doing it. All right, so we're going to construct the sample space. That's the whole point of a tree diagram, is it's a way to help you create your sample space in a way that's structured and organized. And there's a little bit more to it, but not something we're going to cover in our class. But suffice to say, you can move on from this and do more with it. So we're going to create that sample space. So we're going to start off with what we had before, and then we want to expand upon it. So let me draw it for you 1 second. So you can see we have the green arrows and the blue arrows that we had before for the two children example, but now we're going to expand upon that to get the third child, which is the pink arrow set. So again, imagine you're over here on the left, that's the present time, and you're going to hypothetically imagine yourself moving into the future, and that's the first child, male, or hypothetically moving into the first child being female. So imagine your first child is male, and then hypothetically think, I could have another one, and that second child could be male or female. So it could be M or it could be F. Then imagine again into the future even past that. So suppose I did have a male and I did have a male. So I had male as my first two children, and then I could hypothetically think about a third one. Well, I could have an M, right, a male, or an F, a female. So it leads me to M, M, M as one combination, M, M, F as the next combination. Now you'll notice a couple things about this diagram. Again, it's moving into the future as you move to the right. Further into the future, the farther right you go. The numbers and letters, the letters are vertically aligned. So my M is over my F is over my M. It's not all fan shaped, right? So you can get dinged points for that. It should look pretty much like this. And then this M is over this F and so on, right? So it's a vertical alignment. We're close enough to it. Every single one of these end branches, so this M right here has a way that you got to it. Sometimes I'll have students that get confused about this. So I say, imagine this M, how did you get there? You got there from this M, which came from this M. So M, M, M is how we got there. If you're at this F, you got to that F by going M, M, F. That gives you the next one. Then this M, how did we get there? Well, we got there from an F right here and an M right here. So M, F, M. This F right here, we got from this F and this M, so it's M, F, F. Then the whole bottom half of the diagram has a female as the first child. So imagine a female first child, and then M, so female, male. Oops, sorry, I can't click on that one. It's not letting me. So male, and then another male, right? Or this F came from the M in the middle, and then female. Or this M right here came from this F down here and this F right here, and so on. That means you have a sample space created, which is right here. It has 8 outcomes, and they're all listed in order, and they match up to one of these little end branches. One of these little end branches right here makes each one of these. So this first one makes the first one in the list. The second one makes the second one on the list, and so on. So you don't get full credit unless you have the list fully made at the end. So F, M, M, and so on. Now, the assumed probability for each of these outcomes, well, let's think. There's 8 outcomes total, right? 2 for the first child times 2 for the second child. That's why, right, 2 branches in green. Then from this M right here, branches off into 2, or this F right here branches off into 2. So 2 times 2 makes 4. And then from each of these, there's another 2 branches. So 2 pink ones, that's 2 times 2 times 2, that's 8. And sure enough, there's 8 outcomes right there. All right, so 1 out of 8. So each outcome on its own, right? Each one of these individual items in the list, that's what they're talking about. Each of those outcomes has a 1 in 8 chance. Because we assumed that male female were equally likely, then the probability of each outcome is 1 out of 8. All right. Now, what are the outcomes in event H having at least one male? All right, so if you have at least one male, that's male, 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 there's at least one male in there. MMF, there's at least one male in there, and so on. MFF, there's at least one male in there, namely the first one, and so on and so on. All of them have at least one male except for FFF. That'll be an important idea later on in another section. But for right now, let me just type up. And again, notice they want you to list them. They're not asking for the probability. They just want you to list all of the outcomes. In fact, I'll highlight that word list. And if I did this right, there should be 7 of them. Yep, there they are. Right, it's everything in that list except for FFF. Now here it's asking what is the probability of H, right, of this event H having at least one male. Well, there's 7 outcomes out of 8 total, so the probability would be 7 out of 8. All right, there we've got that. So now, this is more hypothetical thinking about this question because I'm going somewhere with this. So the tree diagrams above, I mean, they worked fine for 2 and 3 kids. I mean, they're a bit tedious. You could do 4 kids, you figure, or let's think back to my true-false question, or let's say this was tossing a die. I mean, you could do a couple dice like this. However, would you really want to do this for 6 kids? Let's just think about that for a second. If you had 6 kids, let me back up. 2 kids, it was 2 branches times another 2, right? 2 times 2 got us 4 outcomes. First, think of it this way. The first child, there's 2 outcomes, M and F. Second child, there's 2 outcomes, M and F. 2 times 2 makes 4. For 3 kids, it was 2 times 2 times 2, which is how we got 8, right? There's 8 possible outcomes right here, right? 2 for the first, 2 for the second, and 2 for the third. But if you were going to do 6 children, that'd be 2 to the 6th. Let's just think about that for a second. 2 to the 6th branches. That would be 64 branches that you're trying to fit on a sheet of paper. That would be really tedious, right? We don't want to do that. So we need another way to deal with this. We don't want to do tree diagrams for all sorts of big ones. Tree diagrams are really useful for small data sets, small sample spaces. So we want something that'll be small. Or excuse me, something that'll work even for large sample spaces. Right? Tree diagrams are good for small sample spaces. So, and that way that we're going to use, and I mentioned it earlier, is the multiplication rule of counting. It's how we're going to get out of having to deal with these really ugly large spaces. So remember, all of this, all tree diagrams and the multiplication rule, is to help us with our classical probabilities. Classical probabilities are actually wicked hard. And one of the things that's hard about them is you have to figure out your sample space so that you know the denominator of your fraction, the bottom part, right? So the 8, if you will, on this problem. Like the 8 came out of knowing how big this sample space was. Well, you can do that either with a tree diagram, which is what we did here, or you can do it with the multiplication rule of counting. But you've got to come up with some way to hypothetically imagine how big your sample space is. Keeping in mind that everything is from logic and hypotheticals. It's not from data, which is empirical rule. If it was from data, then you'd know all your possible outcomes because you'd have data on all of them. But for classical, because you're imagining all of this stuff using logic, you need a way to come up with how large that sample space is so you can have a denominator for your probabilities. All right, so we've done tree diagrams, so now let's see this multiplication rule of counting business. And you could hear it when I was going over it. It's the 2 times 2, 2 to the third, 2 to the 6th. That's the multiplication rule of counting. It says, hey, if you've got, P ways to do the first thing, Q ways to do the second, R ways to do the third, and so on, then your task can be done in P times Q times R different ways. And this is how we find our sample space. 2 times for the first kid, 2 for the second kid, 2 for the third is 2 times 2 times 2. So on. If you have 2 to the 6, or excuse me, if you have 6 kids, assuming only male, female possible, then that would be 2 to the 6, which is 64 different ways. And so that would be your sample space size. And I just made a little note up here about why that's so important. Super important note that when you find your sample space size, and that's your denominator in classical probability, that's why it's so important for us to be able to find this, even without a tree diagram, because you would not want to make a tree diagram for this. That would be just horrendous. All right, so let's suppose you're going to toss a coin, a fair coin. So actually, it doesn't even have to be fair. It could just be a coin, as long as it's got heads and tails. So speaking of which, heads and tails. So there's 2 outcomes for the first toss, 2 outcomes for the next toss, 2 outcomes for the next toss, and so on. Well, as a matter of fact, let me rewrite this one. Oops, sorry, in the same way that I just talked about the last one. That'll help you see it. So it's 2 for the first, 2 for the second, 2 for the third, and so on. So for this one, it's actually even simpler because you have 2 for the first toss, right, heads and tails, times 2 for the next toss, heads and tails, times 2 for the next toss, heads and tails, and 2 for the last one. So that's 2 to the 4th, which is 16. All right, now will they always be 2s? No, of course not, right? That would make things way too easy. So suppose I had a fair 6-sided die and a fair 20-sided die. And I know what you're thinking. You're thinking 20-sided dice, do those things exist? Yes, they do. And remember, a picture of them is on your in your exam notes packet that will be given to you when you go to take your test. So a 6-sided die is what you all kind of think of probably when you think of a die. It's a cube, it's numbered 1 through 6. Sometimes they're with dots, sometimes they're with numbers. A 20-sided die is down here. It's, I believe, a dodecahedron, in case you're interested in the geometry of it. So it's a 20-sided die. It's got numbers 1 through 20 on its different sides. There are different kinds of dice even than these ones, but these are the 6 most common kinds of dice. In particular, obviously, the cube die is the most important because it's in most games like Monopoly and Settlers of Catan and stuff like that. All right, so if I'm going to take my 6-sided die, which has 6 outcomes, and my 20-sided die, which has 20 outcomes, and I'm going to multiply them. So the first die is 6 outcomes, the second die is 20. 6 times 20 is 120. Easy as that. All right, well, let's take that 6-sided die and play everybody's favorite game, Yahtzee. All right, so if you play Yahtzee, you're tossing 5 6-sided dice, right? You're trying to get them all to match. That's the game of Yahtzee. So 5 6-sided dice would be 6 times for the first die, 6 for the second die, 6 for the third die, because they're all the same. They're all 6-sided dice, and there's 5 of them. So that's 6 to the 5th, which is 7,776. And if you don't believe me, there. See? All right. Now, what about selecting 3 cards at random from a standard deck? And we're going to do this both with replacement and without replacement. Okay, with replacement means you stick the card back in. So it's like you're playing against a magician. They have you pull the card out, you look at it, and then stick it back in the deck. That's with replacement. So if you're doing with replacement, there's 52 cards in a deck. So let's remind ourselves that. Note, right? 52 cards in a deck. Right? If you're sampling with replacement, there's 52 for the first card, 52 for the next card, 52 for the next card, which would be 52 to the third, which would be 140,608. Again, I can prove it to you. 52 to the third. See? All right, but I mean, let's get real. What kind of card games do you play where people are actually sticking the thing back in there? And like, nobody is, right? Not unless you're playing against a magician, which you wouldn't really be playing against a magician anyway. They're magicians for a reason. They're very good at cards. So let's try without replacement. Without replacement means you draw it and it's in your hand and it's no longer in the deck at that point. Well, that means there's 52 options for the first card, but then once you have one of the cards in your hand, there's only 51 left in the deck. If they deal you another card, then there's only 50 left in the deck, which means it's 52 times 51 times 50, which is 132,600.